Hello everyone, welcome back to our Post-Quantum Cryptography lecture. Today we are dealing with dilithium, and the foundation of dilithium is another signature scheme which is called Schnorr, or by Schnorr. And this is why we directly start with this signature scheme. Okay, let's write it down. So the protocol, which is called Schnorr signature, and as always when we have a kind of protocol, we write down our two actors. On the left hand side we have Alice, and on the right hand side we have Bob. And the goal is that Alice signs messages and Bob can verify these messages. What is the algebraic structure of the Schnorr signature scheme? So the algebraic structure is based on a group with respect to multiplication. So we have a kind of generator which is called A, and it's a generator of a cyclic group. And both actors, Alice and Bob, they both know about this system parameter. So now the first step with Alice is to define keys, starting with the generator. And the key generation is very easy. We have an integer, a positive integer. It's a power of A, so we use it as a power of A. So that means A multiplied with A in a row s times, which is a more or less exponentiation. So we get T is A to the power of S, meaning we multiply A S times. So, and this is the key. You can say this is the private key, and this one, the T, is the public key. And like always, the first step is, after generating the public key and the private key, we need to transfer the public key such that Bob can be sure that T is really a valid public key of Alice. So this is kind of authenticated. This is authenticated, and then Bob verifies. So this can be done via certificates, ordinary public key infrastructure. So now the actual protocol starts. So meaning we have a message, and Alice wants to sign this message. And the first step, what Alice does is to choose a random Y. It's also used as a power like the S, the private key. And then Alice computes a W, and this is the power of A Y times. So, and then we have a hash function. That means we are writing M and W next to each other, so it's a kind of concatenation. And no, it's deconcatenation, to be honest. And then we hash it, and we have another part to compute, which is Z, and this is Y plus S times C. So because we can read the C or interpret the C as a number, So then the signature generation is done. We have the message and we have the two-part signature, which is C and Z. And then we transfer message plus signature to Bob. And Bob now has to verify the signature, and this can be done the following way. We just write it down. Afterwards, we will also prove that this is valid. So what happens? Bob computes A to the power of Z, then the public key to the power of C, and then inverts it, and this product yields W prime, and this W prime should recompute the W. And if this is the recomputation of W, then we just have to follow and compute the corresponding C prime, which is hopefully then the C part. So if C is equal to C prime, then we accept the signature, else we reject it. So, and this is the protocol. What else can we say about it? So we have a hash function, and the security more or less belongs to an DLP. Let's say here. So computing the S value from T is a DLP, discrete logarithm problem. Okay, let's prove that the verification really accepts or rejects the signature. So for that, we've stated a kind of lemma, and the lemma says the Schnorr signature is correct. Scheme is correct. This is what we want to prove now. So putting some fancy frame. And now the proof. So how does the proof work? Let's start with A to the power of Z. So A to the power of Z can be reformed or restated by putting the Z value, which is Y plus SC. This was in the signature generation part. So this is Y plus SC. Actually, I forgot to put one thing, or this is not really necessary, but how to consider it, that Z and Y and S are powers of A, and A generates a cyclic group. So this can be considered mod the order of the cyclic group. So the Z can be considered this value modulo the order of the cyclic group. So we can also write it like this. The order, the cardinality of the group generated by A. Okay, let's now work a bit on this. So if this is the power, we can simplify by writing this and A to S to C, and then we check what we have. So in the signature generation process, the A to the power of Y is W, and A to the power of S is here, is the public key. And so it's T to the power of C. So A to the power of Z is W times T to the power of C. Yeah, this can be equivalently formulated as A to the power of C times Z to the A to the power of Z times T to the power of C, but the inverse, because we bring it to the other side with the inverse element. And if we now call this the W prime, then we have exactly what we do in the signature verification process. So this is actually true, that W prime gives W with the aid of the public key and not with any other. So furthermore, we can use the hash function now. So if we take M concatenated with Y with W and W prime, then it's the same. And of course this works is under the assumption that H is collision resistant. So this is C and this is C prime. So C is equal to C prime. So this finally, that the check is correct. Okay, so this is the major part. We have the Schnorr signature scheme, and from this scheme, which is correct, we are developing another scheme, which is finally the dilithium scheme. So let's call it like from Schnorr to dilithium. So and to do so, we just recap all the necessary parts of Schnorr, and then we try to explain how this changes. Let's start with the keys. Again, we have the keys. The keys can be written like this. This is the key. And we immediately do the dilithium part. So this part in Schnorr is an exponentiation, a multiplication of A. And in dilithium, we replace this group multiplication by matrix vector multiplication. So in dilithium, we take it matrix A and a vector S. So I leave a bit more space because this doesn't work in the moment. We will see that this doesn't work because this is not a hard problem. This is an easy problem. To recover S from T is easy. It's just solving the linear system of equations. But for now, it's okay to leave it like that. So in the signature generation process, we compute W, which is a to the power of a random Y element. Then we have the hashes and the second signature part component, which is this. So this is actually keys first, then signing process, and yeah, finally we have the verification. And the verification was done by computing the A to the power of Z, T to the power of C inverse, and this should give W, or gives W if everything is correct. And then we compute this and check. So this check can be done. This is verification in Schnorr. So now we replace the group operation. So in dilithium we could do it the same. So let's say we compute A to A times Y, and Y is a vector. Then we compute the C. This is nothing fancy, it's just a hash operation with concatenation. Leave a bit space here. And the set is completely the same. And with a verification, so we think about this. So the W, need a bit more space. The W prime computed on the left hand side was like an A times Z, A to the power of Z, which is replaced by A times Z. And here it's getting a bit different, but not so much. So we have T to the power of C in Schnorr, which is equivalent to multiplication. It's a scalar multiplication of the vector T times C. And on the left hand side we have the inverse of the multiplication, which is to the power of -1, and here we just put a minus in front of it, in front of the expression. So, and this gives, we can see this gives W, and the rest is the same again. And finally we have to compare C with C prime. So it could be so easy just to replace the group operation by matrix vector multiplication. But the reality looks a bit different. So this is an DLP, and as I said on the right hand side in dilithium, so if we leave it like that, so the problem is not a hard problem. So we have to make it to a hard problem by adding some noise. And in this case we get this to be an LWE problem, learning with errors problem, like we had in the Kyber encryption system. So, but if we add now this noise, so the protocol a bit changes exactly at this position here, that we get an C times S prime. So this noise just affects this equation. And now the problem is obvious. So the problem means that if there's a noise, and this adds as well in the equation to the W, in this case minus CS prime, we get that W prime isn't W. And that would mean that the signature verification fails, because C can never be C prime. And to overcome this problem, we need some kind of error. We need error, a bit more space. Robustness. Meaning we need a kind of function so that Fw is the same like Fw prime. So that this small noise, C times S prime, that this is somehow removed. And if this is the case, so we can just tweak the protocol a bit and just put here this function, this secret function we don't know yet, but I can say that this function exists, and the next goal is to work on this function. So, but if we formulate this protocol, the dilithium protocol, like that we add this function before hashing, then we get an error robustness, and this small part, the minus C times S prime, that disappears. And now we can verify the signature again. So the goal now is that we want to study this function. And we want the condition, in particular the condition under which this function provides some error robustness. Okay. For that, we define two functions. So for the function, we consider elements of set Q, and we have an, let's call it alpha. We have a second parameter, which is smaller or equal to Q. And the first function we define is high of W alpha, and what we do is we round just the value W divided by alpha to the next integer. And the second function is called low, and low means we compute the symmetric modulo. W S mod alpha. So on the first thing, the high function, that will be our f. And the low function, this maintains error robustness. If this value satisfies a certain bound. So a quick remark that having these two functions, and in case of dilithium, we have not only elements in ZQ, we have elements in RQ, which is the extension of ZQ. And furthermore, we have not only elements in RQ, we have matrices and vectors over RQ. And by considering low and high, which is now defined over ZQ, we can also extend this to RQ and the vector space over RQ. So high. High and low function can be extended component-wise to the ring RQ or RQ to the power of k, the vector space. Okay, so after this is done, after this definition, we get some important results on how high and low belong to each other or are related to each other. And the first one is I call it lemma again, and this finally states that any W can be combined from high and low the following way. So high of W times alpha plus low of W gives the original element. Again, I like to put some frames around the lemma. And again, we prove it. And maybe one thing I have to add. So if we want to consider this equation, we can solve it for high and finally get that this is the same like high, I leave out the alpha, is the same like W minus the low value and then divided by alpha. Okay, so let's prove it. So this is equivalent to the stated version. Okay, now what we have from an earlier lecture, I guess it was lecture 1, we have that we consider the W divided by alpha, the rounding function on that. Then we get two cases. We can express it with a floor function. And this applies if this is valid. Or we get the floor function +1 otherwise. So this is what we need actually for the proof of this equation. So if we have W and we divide it by alpha, we get by division with remainder. Just the ordinary division with remainder theorem. Forgot D. Remainder. We obtain the W is the same like the floor of W divided by alpha. This is the integer part times alpha plus the remainder. The remainder is nothing but W modulo alpha. And of course, if we consider this part and this part, and we have the case that W mod alpha is smaller than alpha to alpha half, what we get is that this is actually already the symmetric modulo value, which is finally the low part. Going back to the definition, we have here the low, and considering this equation, we get that this is exactly the rounding, and the rounding is nothing but the high part. So we have it here, the high part. So this is done. So in the case if W modulo alpha is smaller than alpha half, so it's valid. So this equation that the high part times alpha plus the low part is exactly the original value W. But what we can also do from this equation, we can just add and subtract alpha. So we first add it. Plus alpha, and then we have W mod alpha minus alpha. So in the case, let's say in the case, I write it in another color like yellow. If W mod alpha is bigger than alpha, bigger or greater or equal to alpha half, then we have first another thing to do. I just put the alpha into this bracket. So make another bracket around this. And in the yellow case, so this gives according to the equation here, we get also the rounding. And this part, by definition, is the symmetric modulo as well. So in both cases we get this one. Which is exactly the high part and the low part. And this is how the proof is done. I guess it's quite reasonable to consider one example for the high and the low and this redecomposition of this W. So, example. Okay. The values we consider is Q is 32, the alpha value is 8, and we start now not only with a ZQ element, we just take an RQ element, so it's a vector in ZQ elements, and we take 3, 5, 11, 31, and now we compute high and low, and then we show that the combination again computes the W. So the high part of W alpha, let's write it down. It's the vector 3, 5, 11, 31, 8, and yeah, we used the rounding. So divided by 8 and then rounding. So we can 3, 8. 5 divided by 8. 11 divided by 8. 31 divided by 8. And yeah, this gives, and rounding then, yeah, it gives 0. 0, sorry, 5, 8, 5 is closer to 8. That means 1, 11, 8 is 1, and this is close to 4. So we get this vector. So the low function like low of 3, 5, 11, 31, 8. Now, yeah, we apply the symmetric modulo value. S mod 8, 5, S mod 8, 11, S mod 8, and finally 31 S mod 8. And yeah, so the modulo applies, or in the S mod case, we subtract the value by 8 if the value is bigger than 4. So, and we leave it if it's smaller. Okay, that means 3. That means it's bigger than 4, it's 5. Then we subtract 8, it's minus 3. 11, then minus 8 is 3. And then 31 S mod 8 gives finally minus 1. Yeah. Okay. So we consider now the recomputation. Put it together times alpha plus low W alpha, and this is 4 times 8 plus 3 minus 3 minus 1. Computing 0 times 8 gives 0, gives 8, gives 8, gives 32, which is modulo 8, 0, plus minus 3 minus 3, 3 minus 1, and so 0 plus 3 is 3, 8 minus 3 is 5, 8 plus 3 is 11, and 0 minus 1 is minus 1, minus 1 plus 32 is 31, if we consider it in the ordinary representation from 0 to 31. So comparing, so the original value we have here, and we can see that it matches exactly here. So this is W. Okay, this is now an example how this high and low works, and that we can recombine the W value. And as I said, we go back to the protocol, here, and what we want to have, that it's the high value of W prime is the same like the high value of W, meaning that this kind of error noise cancels out. And the condition that this works, this gives the final lemma. The final lemma of this lecture. So the proof again is a bit long, but we go through the details. The lemma we are not formulating, stating it in the RQ or RQ to the power of K case. We just use the simple case like we did for high and low definition. Just consider about ZQ. Okay, we have A, alpha, not A, alpha. Then we have W and E in ZQ, and then we get the following condition. So we have low, the absolute value of low W alpha. Oh, sorry, I want to subtract E first. And if this is smaller than this, we achieve that the high value of W minus E is the same like the high value of W. So this noise, this E, this minus E, disappears. It's robust against this kind of noise. So the proof for this the proof is, it's not so complicated. It's just a few few equations about the absolute value and using the definition of high and S mod. So, and then finally we get the result. So let's start and consider the W minus E, and we consider it in the symmetric representation, and of course this is finally the low value. And as we know, symmetric modulo is more or less the same like normal modulo, just the case that minus alpha or multiple of alpha is subtracted. So what we get is that S mod alpha minus E, and we have this factor that for some integer alpha is subtracted. For some set in set, element set. Okay, so the modular operation in a sum, they can just be applied to all these individual terms. And this is the same for S mod. We just have to be sure that in some cases alpha, for some set, alpha is subtracted. Okay, this is equivalent to, yeah, as I said, low, just the definition. And this is the definition of W minus E minus set alpha. And we bring it on the other side. We just solve this equation for low W. And we get set alpha plus low W minus E alpha plus E. We can put here some brackets around, and we now assume that the set value is non-zero. So we use a proof of contradiction. We show that this cannot be true, that the set is non-zero, but we assume it, and then we show that there arises some problem if we put the set non-zero. The first step from the last equality is that if we put some absolute value around this one, and here like this, so we can apply the reverse triangle inequality, and then this changes a bit. So this becomes greater than or equal, and we put it here and gets a minus. So this is the reverse triangle inequality. And yeah, we just since alpha is a positive integer, we can put the set this position. So this is the first one. And what else can we do? We can assume that this is greater than or equal to alpha minus low W minus E plus E, because we have the case that Z is non-zero, so the absolute value of Z is then, yeah, greater than or equal to 1. So this is true. And what we else have is this equality. So we consider this part. And if we consider this absolute value, then this is by triangle inequality. We can write it like this. And this one, we know. This is the precondition. So if we put this E with plus on the other side, we get this less than alpha half. So it's alpha half, and this is, of course, alpha half as well. So putting it together in one line, we get that low W alpha is less than alpha half. Yeah, that's wrong. So from this one we get that is greater than alpha half. What I wanted to say is that this is a contradiction, or because of the definition of this law, we get this. This is a contradiction. Make it in red. It's a contradiction to the fact that low alpha is less than alpha half. This is just by definition with a symmetric modulo. So if we have the symmetric modulo, we have to put the absolute value around it. So this is the definition of the absolute of the symmetric modulo. Okay. So what's the conclusion? The conclusion is that the assumption was wrong, meaning that Z is 0. And this provides this equation. Just going back. So here this part, or here, write it here, this part, this disappears if Z is 0. And this is the result. So we can express the law of W minus E by the law of W minus E. So, and this has some effect on the high value. If we consider the high value of W minus E, we can rewrite the high value by W minus E minus the low value. Let's go back. This was just this equation, this one. Going back. And yeah, we can replace the low W minus E minus its low minus E and we see that minus and minus gives plus, and then this cancels out with the minus E, and we have W minus low double W alpha left. And again, this is the definition of the high value of W. So, and then meaning that the proof is finished. So this was the lemma stated for elements of ZQ. And again, this can be easily extended to elements in RQ and the vector space, because we just have components to consider. So the previous lemma also holds for RQ and RQ to the power of k, the vector space. If we replace the absolute value by the infinity norm. As I said, just by considering component-wise the elements. Another important result I state is that when we go back to dilithium, we get the case that, or we get the condition under which the high value of W and W prime is the same. So in dilithium we obtain the high of WCS alpha is the same like the high of W and yeah, whenever the norm, the infinity norm of the low part of W minus C S prime is smaller than alpha half minus B, with the fact that the norm of CS is smaller than B. So, and this is in the protocol of dilithium, we have to check this condition. So by choosing S prime and C, we get that this is a norm, this is under below a certain value, and this one, yeah, is system parameter. And if we can assure or ensure this bound, then yeah, everything is fine, and the high values are robust against this noisy part. So this is our final result of this lecture. The conclusion: what we finally can say is that the dilithium owns the structure of Schnorr over RQ, and yeah, we have some rounding to maintain robustness. So the outlook for the next lecture is we write down the dilithium protocol, plus some modifications. The modifications, they provide some optimizations and some security related things. So thank you very much. This is the end of today's lecture.